Should I start?
I still see a few people trickling in. Maybe let's give it till just exactly like maybe just 1 more minute, if that's okay.
Do I share the right screen?
Yep.
Okay.
Actually, it looks like the number of participants has stabilized, so maybe we can move forward. So welcome back, everyone. The first talk will be given by Maaike Werdesteijn on modeling viscoelastic solid earth deformation due to ice age and contemporary glacial mass changes.
Thank you, John. So my name is Maaike, and I'm a PhD student at the University of Oslo. And I'll present some work I've been doing with James Conrad, with John, Timo Heister, Joshi Zhang, Rebecca Steffen, and Jesse Reuse. So why is the Earth deforming? It's deforming due to past and present ice mass changes, and the deformation is controlled by elastic and viscous Earth material parameters. So here you see a simple schematic overview that where we have an ice sheet, we see subsidence and coming from sort of an elastic or flexural response from the crust, and on longer time scales, mantle material flowing away from the area of glaciation. And then when the ice is melting, or when it's already when it's been gone for a while, we still see uplift in the area of previous or in the area of deglaciation. So that is the one component in glacial isostatic adjustment. And the modern field of glacial isostatic adjustment, or GIA, addresses not only the solid earth response to surface load changes by ice, but also by ocean water, and then the gravitationally consistent redistribution of seawater across the global ocean. So why do we model GIA, or solid earth deformation? So there's a lot of geodetic observations that contain this GIA signal, which is a vertical land motion from GNSS, absolute sea level from satellite altimetry, relative sea level from tide gauges, and then mass or gravity or mass changes from ground basin satellite gravimetry. And so let's focus on GNSS measurements. So the present day deformation and deformation rate we measure is a combination of the elastic deformation coming from contemporary ice melt and a signal of viscous deformation coming from ice melt over the last glacial cycle. And in order to find the signal related to contemporary ice melt, you can correct these GNSS observations for the viscous deformation. And for that, you need to model this component, or vice versa. You can also correct the data for this elastic deformation based on other geodetic observations of mass change or ice mass loss, and then find the viscous deformation. But one component that is often not considered is the viscous deformation in response to contemporary ice melt. And this will only be present, or this will only take place if there is a low viscosity region in the upper mantle. And we actually do think that these areas exist in Greenland and Antarctica, and that is quite interesting because those are also locations where there's past and present ice melt. So we have this mixed signal. So in this presentation, I'll show benchmark study of solid earth deformation in aspect or parts of it. And then after that, we'll take a closer look at Southeast Greenland and observations of uplift rates from GNSS. So this is part of the benchmark. So on the left, you see here we see a 3D box geometry using a viscoelastic rheology, a free surface on top. And we model here, we use an axisymmetric model using free slip boundaries. And then this purple thing here is a quarter cylindrical ice load that we model over a short time scale simulation. So we let the ice increase in 100 meters from 0 to 100 years, and then keep it constant for another 100 years. And then also a long time scale simulation where we model it over sort of like a rough representation of the last glacial cycle. And then we compare deformation with two other codes, and those are taboo, which is open source. It's semi-analytical, so we can only model layered earth structures. So we cannot use that code in the presence of like lateral viscosity variations. And then we also compare against a code in Abacus, which is also finite element based, but it's commercial. So here we see some of the results of the short timescale simulation. The upper three plots here show the vertical surface deformation as a function of the distance from the load center. So here's the load center. And for aspect, taboo, and abacus, and you see from a first view that they're very similar. So there is more like deformation taking place over the first 100 years, because that's when the ice is increasing, and then the other 100 years, the ice is kept constant. And then in the lower left, you see the maximum vertical surface deformation as a function of time. So the maximum is here underneath the load center. For the three codes, also look very similar. And then we look at the vertical surface deformation as different distances. So at red is underneath the load center, yellow is 100 kilometers away from the load center, which coincides with the loading boundary, and then blue is 250 kilometers away, which is even further away from where the ice loading is changing. And then the deformation and deformation rate. And there is some small differences, but also, yeah, there's a lot of, they look very similar. And then we do the same for the long timescale simulation. So the main conclusion is that the maximum deformation and deformation rates using aspects agree within like 2.5% for the average percentage difference with taboo and abacus on glacial cycle and contemporary ice melt scales. So that gives us a lot of confidence in our code. And we also demonstrate the, not shown here, but computational efficiency of using adaptive mesh refinement. And that is a nice advantage for solid earth deformation modeling when ice loading is changing at different resolutions at different times and locations during the loading history. And then we also did a short application using a this lower viscosity region underneath the ice loading in combination with the adaptively refined mesh. And then we can only compare to abacus, because in taboo we cannot include lateral viscosity variations. And then, yeah, again, we see a very good agreement. But the more fun part is actually applying this code to an actual region. So that's what we're going to do next. So we're going to look at GNSS uplift rates in Southeast Greenland. So Greenland passed over the plume, the Mantle plume that's now located where now Iceland is located, more than 40 million years ago. And from a variety of geophysical observations, there are indications of a low viscosity mantle or a weakened lithosphere underneath Greenland. So in this figure from Martels et al., it's a summary of proposed plume tracks or hotspot tracks. So how Greenland moved over this plume. And the black one is the one they proposed in their study, and that's the one we will use as a reference. So we find very high uplift rates in Southeast Greenland. I don't know if you can see my mouse, but yeah, okay, that will be there. And they cannot be explained with Earth models that are radially symmetric. And we also found in one of our studies that in the presence of a low viscosity region, in the Mantle, the contemporary ice loading changes generates, next to the elastic response, also a viscous response on short timescales, which can be much larger than the elastic response. So definitely like a factor we need to take into account. So how do we do that? On the left, you see Greenland, and the orange dots are all the GNSS stations in Greenland. The black line is the plume track that we showed before, and then this teal box is the area we're going to model in aspect. And on the background, you see mass change over 2019 from a satellite altimetry derived product, which we will also use as over like 25 years as one of our loading histories. And then in the middle figure, we zoom into this region, and we're going to look at 4 locations, 4 GNSS locations. And the yellow, orange, and red color, they indicate the different plume track widths that we're going to model. So from 200, 400, and 600 kilometer different widths. And then on the right is like a schematic drawing of a cross section of the plume track, where we have the lithosphere, a layer of the upper mantle, and the plume track. And then where the plume track is located, we also model some lithospheric thinning. Yeah, so what are the variations we're looking at? I already said the track width from 200, 400, and 600 kilometer. Then we also vary the plume track viscosity and the lithospheric thickness from 30, 60 to 90 kilometer. And we have to model different time periods because the Earth is still deforming from ice that's long gone. So we model the modern changes from mass change derived from satellite altimetry. And then we also have like a rough mass change estimate from the year 1000 to 1995, which we'll model over that time period. And then the glacial cycle ice change. But we also have to use a global model because the Laurentide, so the North American ice sheet, also has an effect on uplift in Greenland because it's located on the peripheral bulge of the bigger North American ice sheet. And then we also model that timescale regionally with aspect. And there is this like elastic long wave component in of mass change of like all the mass in Greenland that we're not modeling because it's outside of our region, but still has a small influence on what's happening inside this region. So here's a few examples where here we vary the track viscosity, and we keep the track width constant with 400 kilometer, and the lithospheric thickness is 60 kilometer. And so you see the surface displacement rates. It's going up, and if it's subsiding. You can clearly see here that for a lower viscosity, there is a sort of like a wider region of uplift, which is strongly associated with the ice change, and also for like a higher plume track viscosity, you see that the uplift is much less. And then I also show that for having different track widths, so it makes sense that when you have a larger track width, then that uplift signature will also spread like over a larger region and will show a stronger uplift. But what we can do next is that we combine all these different options of the track viscosity, the lithospheric thickness, and the track width, and then compare to the 4 station observations of uplift rate. So that is the next slide. On the y-axis is the surface deformation rates, and in the columns here are the 4 different station locations, and then the different colors and symbols indicate the track viscosity and width, and then they're also divided in smaller columns of lithospheric thickness. And the black dot with the arrow bar here is the observation of uplift at each of these locations. So you can see that at the location here, which is actually located at one of the largest outlet glaciers in Greenland, so where there's a lot of ice mass loss, that we can match observations with a lot of different Earth model or like track models for viscosity and lithospheric thickness and track width. And we can also see that the station located much closer to the ocean and further away from this outlet glacier, we can only match observations with very low viscosity, so that's the red, and relatively wide track width. And we also see that this station here is fairly unaffected by whatever parameters we use for the plume track. So that could be that something is not captured in one of the ice history models that we're using. Yeah, so that's the status so far. Yeah, any questions? Or later?
Great. Thank you, Maaike. And I think to keep on schedule, we should move forward, but please go ahead and put your questions into the chat, or we can discuss them live after the next two talks. Great. And the next talk will be given by, let me quickly bring up the schedule. I believe it's Valeria. Valeria, please go ahead and share your screen as soon as you're ready.
Yeah. Okay. Can you see everything?
Yep.
Fine.
Yep. Please go ahead.
Okay, great. So hi, I'm Valeria. I'm a PhD student at the University of Miami, and today I'm going to talk about slab temperatures in 3D dynamic subduction models. So the idea at the base of this study is that if we look at processes that take place in subduction zones, we see that they are highly temperature dependent. For example, if we look at the slab as it subducts into the mantle, it gets in contact with warm material in the mantle wedge, and we're going to have various reactions, among which dehydration reactions that are going to leave the slab a bit weaker than it was before, and this is going to cause seismicity. The volatiles that are released in the mantle wedge are going to facilitate melt production and eventually generate arc volcanism. And then, of course, we have metamorphism in the slab itself. So all of these processes, we said, are highly temperature dependent, and they are also highly variable, both in time and along strike. And as of now, we have very limited ways in which we can probe temperatures in subduction zones. One of them is through metamorphic rocks, so we can look at exhumed metamorphic rocks, calculate their pressure temperature conditions, and reconstruct their thermal history. But more often than not, what we do is to use subduction models. And in terms of literature, these temperature variations have been studied quite extensively. And in particular, we can look at how they evolve in time or along strike separately. What we are trying to do here, however, is to build a physical framework to understand how temperatures evolve simultaneously in time and along strike, since we see that that is what happens in nature. So we're basically trying to see what happens for early versus mature subduction. And in terms of along strike variability, what we want to look at are the effects of plate mobility. So what does it happen if both our plates are free to move, or if we fix one of them, and plate width. In particular, we are looking at these two things for the along strike variation, because if we look at a map of subduction zones, what we see is that, for example, in the Caribbean or South America, we have plates that have very, very different dimensions. And if we look at velocities, and this in particular is a map that shows trench motion in an absolute reference frame based on the direction of mid-ocean ridge spreading, we look at the aleutians up north, or at Tonga Kermadec, we see that the aleutians are basically stationary, while Tonga Kermadec has higher trench velocities. One of the ways in which in the models we can control trench motion is through plate mobility. So these are the two main things that we look at in terms of a long strike variation. For the rest of the talk, I'm actually just going to talk about the plate mobility case for the long strike variation and how it evolves in time. What we find in the results is that basically, regardless of plate mobility and plate width, the temperatures vary in the same way. So I'm just going to present one of these two things right now. So we study temperatures using aspect. This project started a while back, like 3 years ago. So we were using version 2.1.0. And we modeled 3D fully dynamic subduction, which means that we can, at the same time, once again, look at along strike variations and time variations in temperatures. We solve the usual equations for mass, momentum, energy, and conservation using the Fields method in the Business approximation. And our model domain looks like this. So we have a whole plate domain. We have the whole of the upper mantle and a portion of the lower mantle. Our plates are both oceanic with a thermal age, initial thermal age of 10 million years for the overriding plate and 90 million years for the subducting plate. We also have a weak 10 kilometers crust in the subducting plate that allows the two plates to remain decoupled throughout the whole model run. All of our boundaries are free slip, and we fix the temperature at the boundaries as well. So we have 0 degrees Celsius at the surface and then mantle temperature on the other boundaries. And the model domain is symmetric. So from now on, every time I'm talking about the slab center, I'm going to refer to this vertical section here. And for the slab edge, I'm going to be referring to this vertical section there. In terms of mesh refinement, as we said, up until now, Aspect has adaptive mesh refinement, which means that we can highly refine just the regions that we are interested in, so where we want to extract temperatures. And in particular, we want to look at the plate interface, so the area where the two plates are in contact, and the slab top. So I can have a resolution of up to 1.8 kilometers there, thanks to Aspect. All right. From the literature, we also know that there are some components of subduction models that will have an effect on temperature. So we want to understand also what is the physics behind these temperature variations. And for this reason, we are focusing on all of these controls. In particular, we are going to look at subduction flow field. So we're going to have a look at how colloidal and toroidal flow, which are the vertical and horizontal component of the flow respectively, impact temperatures. And we know that the flow is connected to slab morphology and its evolution and convergence rate. And then we're going to have a look at the coupling depth. So the coupling depth is that depth that marks the transition between the plate interface, where we have a cold thermal regime, and the wedge slab interface, where the slab is in contact with the mantle wedge, and we have a warm thermal regime there. Generally speaking, in the literature, the decoupling depth is considered as fixed, and this comes out from heat flux measurement. But we are going to consider our decoupling depth as variable with the system as well. So it's going to evolve naturally with our models, and it will depend on the time since initiation and also from convergence rate. So 3 things to keep in mind: subduction flow field, decoupling depth, and convergence rate links everything. So let's have a look a bit more in detail to the subduction flow field. Here I'm showing the evolution of slab morphology and flow field for our 3 models and 3 different times: 14, 20, and 45 million years. 14 million years corresponds to the end of free sinking. At 20 million years, the slab is interacting with the upper-lower mantle discontinuity, and 45 million years is just towards the end of computation. So we have mature subduction. What we can notice is that, first of all, if we look at the velocities are going to be very high. Also, convergence rate is going to be very high towards the early stages of subduction. And then as the slab starts to interact with the lower mantle, everything is going to slow down. The free plate case and the fixed subducting plate case, so if our overriding plate is free to move, basically show the same slab morphology evolution, and the flow field remains, both components of the flow field remain very vigorous throughout the whole model run. While in the fixed overriding plate case, slab evolution is very, very different. We see that as soon as the slab reaches the lower mantle, it just bends backwards, and the flow is very weak, especially toroidal flow. All of these are, once again, the result of convergence rate and the trench retreat that in this case is basically absent. So if we look a bit more in detail at convergence rate and trench retreat, here I'm showing convergence rate solid line and trench retreat dashed line for our models at the plate center and at the plate edge. The 3 main things that are takeaways from these plots are that the convergence rate is always higher at the plate center than at the plate edge, and this is crucial to keep in mind for when we talk about temperatures. The free plate case have higher convergence rate than all of the other ones, and then, as we said, the fixed overriding plate basically does not have any trench retreat, which causes that slab evolution that we saw before. But I also said that convergence rate is reflected in the coupling depth. And here I'm showing the coupling depth and how it evolves throughout the model run for all of the models at the plate center and at the plate edge. So the shaded area in gray corresponds to the range of variation of the coupling depth for all of the models at the edge, and the area in brown at the center. The 2 main things that we want to remember here are that the edge to center variability increases with time. So during the early stages of subduction, the coupling depth is almost constant along strike, while it becomes deeper during later stages of subduction. And at the edge, at the center, it's always shallower than at the edge. So the coupling depth is always going to be closer to the surface at the center of the plate with respect than at the edge of the plate. All right, so we have all of the ingredients that we need to talk about temperatures finally. The first thing we did was to extract pressure temperature paths from the surface to 200 kilometers depth along the slab top. What we obtain looks like this. I'm showing here 3 different times just to see that we have a time evolution of temperatures, and in particular, temperature will decrease as time increases in our model run. And then if we look at the plate edge, which is the dashed line, and the plate center, which is a solid line, we also see that we do in fact have an along strike variation in temperatures. It was a bit difficult to quantify this along strike variation. So what we did was to compute the temperature difference between the edge of the plate and the center of the plate for these 3 different times and at 3 different depths, which are 60 kilometers, 130 kilometers, and 200 kilometers depth. And this is because we want to probe temperatures respectively above and below the decoupling depth. So what we obtain looks a bit like this. In the top part of this figure, we can see the cases in which the edge of the slab has a higher temperature than the center. And on the bottom half of the figure are all of the cases in which the edge has a lower temperature than the center. So what we find when we analyze these models is that convergence rate has a key role in controlling temperatures. And it also really depends on what the absolute magnitude of convergence rate is. If we look at the early stages, in fact, of subduction, what we see is that the center is colder than the edge of the plate. So what's happening here? If we remember from the plots that I showed before about convergence rate, during free sinking especially, the velocity is very, very high, and it's higher still at the center, while the decoupling depth is not really varying. We said that the decoupling depth remains almost constant along strike during the early stages of subduction. So this means that this higher convergence rate at the center and the coupling depth that's not varying make it so we are sinking colder material faster at the center of the plate than at the edge. And there is basically no time to transfer heat to the slab top because the convergence rate is so fast. And this is going to cause a localized decrease in temperatures at the slab center. On the other hand, if we look at the later stages of subduction, we know that after the slab interacts with the upper-lower mantle boundary, everything slows down. We see that the center becomes warmer than the edge. So, as I said, everything slows down after the interaction with the lower mantle. And this slower convergence rate makes it so, in this case, we can efficiently transfer heat from the mantle wedge on the slab top. And the fact that in this case, the fact that the convergence rate is higher at the center of the plate, not by much, but it's still higher, makes it so colloidal flow is a lot more efficient here at the plate center, and results in more transport of warm material from the mantle into the mantle wedge at the plate center. And at the same time, this is also going to push upwards the decoupling depth, which means that we're going to have a shallowing of the decoupling depth. In fact, we see that the decoupling depth is always shallower at the center of the plate than at the edge of the plate. And all of this is going to result in an increased temperatures at the plate center. So this is just a nice drawing to conclude. We see, in fact, that we have an along strike variation in temperatures and that they evolve in time. And in particular, at the center, we have lower temperature during early stages of subduction and then warmer temperatures during later stages of subduction. And basically, this just confirms that if we want to look at how processes that depend on temperatures in subduction zone evolve in time and along strike simultaneously, maybe it's worth it to consider a 3D and dynamic approach to study slab temperatures. And just want to thank CIG and the Aspect developers for developing the Aspect, which is the tool needed for this research. Thank you.
Excellent. Thank you, Valeria. We're right on time, so I would propose we go on to Frank's talks. Next.
Okay, can you hear me? Can you hear me?
Yep.
Did you confirm? Okay, good,
Yep.
great. I'll share my screen and then hopefully you can see the title slide. Let me. Okay, yeah, so thanks for having me here. I'm Frank Zwaan, and I would like to talk a little bit about modeling of mantle exhumation in inverted rift basins, which is a collaboration with various people like Sascha Brune, Anne Gleren, Dylan Vezi, and John Nalibov as well. And this is all based at GFZ Potsdam in Germany. Let's see, yeah. Okay, so we're interested in mantle exhumation, which can happen in different tectonic settings. For instance, if you, to the left here, you can see how you can break apart a continent, where the gray would be the lithosphere, or at least the crust, and the green would be the mantle material rising to the surface. And this is one way of getting your mantle to the surface. Another way would be in a collisional system where you close maybe an ocean, a system like this, where then pieces of mantle are caught in the origin and pushed up to the surface. And this is important for various reasons, not only for understanding tectonics, but also because we would like to apply this for mineral resources and natural resources. So where mantle is at the surface, it's an interesting place to look for these. This can be done by using, understanding this kind of systems can be done by numerical models. And for instance, this is an example of a test model by Sascha Brune, where, again, the green part here is where the mantle gets to the surface in a rift system. And over here, this is a collisional system where mantle rocks are caught in the origin and pushed to the surface. And so this is the idea of this project I'm doing. However, I wanted also to tell you a little bit about my background, because I'm actually an analog modeling expert, if you want. I did a lot of analog modeling in the past, where we try to model these very large-scale tectonic structures on a small scale in the laboratory. And what I've been doing for the best part of, I don't know, something like 9 years, is building these kind of models that you can see here to the left, a basin that you can fill with all kinds of materials like sand, silicon, syrups, to represent the layers of the lithosphere. And what we had in Bern, where I was working before, is that we could put this kind of machine into a CT scanner. You can see here the CT scanner. There are cameras on top to monitor what's going on. And this is the model then, this is the whole machine that can be scanned. And it creates nice images like this, where we have different layers, which is a sand layer, a silicon layer in between, a sand layer again, and a silicon layer representing the upper crust, lower crust, upper lithospheric mantle, lower lithospheric mantle, which is then brittle, ductile, in reality, all on top of a syrup. And you can see what's happening here in real life. You can see how the different layers are deforming. So this would be the mantle here that's reaching to the surface, whereas there is a rift starting to develop here. And of course, this is very cool. This is actually something cutting edge from the analog modeling community. It's impressive in tectonics, if you would be interested. However, there are some limitations to this kind of modeling. And therefore, I went to Potsdam to do numerical models. So I'm switching gears. I'm going to a different domain. And I'm using this aspect code now. And I took one of these models by Derek Neuhardt from the team in Potsdam, which includes things like temperature and surface processes. And exactly these kind of things are quite difficult or almost impossible to implement in analog models. So this is a real advantage. And what I then added, or what we added to this model by Derek, which was mostly rifting before, is this inversion. So we open a basin and then we close a basin. And it looks a little bit like this here, where we have a model that is something like 450 kilometers long. It's about 200 kilometers, or exactly 200 kilometers deep, I would say. There is the lithosphere, or the mantle lithosphere. There's the lower crust, upper crust, and we also have a surface processes model, Fastscape, which was developed in Potsdam as well, I believe, which creates some kind of a quasi 3D model, whereas the tectonic model itself, it's 2D. So this is quite cool, I think. This is one of the videos of one of the early models that I did. It's a little bit clipped here at the bottom. At the top here, you can see the surface. So that would be the surface processes. This is the upper crust and lower crust. And then there is the mantle below. And if we let it run, you can see that we have a rift developing, an ocean developing. And at some point now, it will start to close. And you can see that there are pieces of mantle here that are stuck in this origin. So we are interested in this kind of thing. How do we get the mantle to the surface during rifting already? What's the history of that? And what happens then when you close this system? So there's still this piece of mantle stuck there. And so this looks pretty nice, I think, at least colorful. There were, however, quite a lot of different small issues and problems. So it took a little time to hammer all of that out. But now I would like to show you a couple of results that are going towards towards a real paper, if you want. And we were trying different parameters. And the first of them that I would like to show is the duration of rifting. What you can see here from top to bottom are 2D sections in which, again, we have the upper crust, lower crust in gray and the pinkish. And then all the green is the mantle. So it would be lithospheric mantle and the asthenosphere below. And if we start to rift, you can see how you have a development or an evolution where we have more and more mantle reaching to the surface. So that's already one thing. The more rifting you have, the more mantle material gets to the surface. It sounds quite obvious, I guess, but that's what it is. If we then start to converge again, we start to invert the basin. And what you can see here, if there's no rifting, you get directly some kind of a pop-up structure. After, if you have some kind of a rift basin, it looks still quite similar. But the more you go into a more developed oceanic basin, where more mantle is at the surface, you get very different structures compared to the early, or the systems that have no rifting at the top. You can make time steps, and you can see how things develop over time. And it's very clear from these models that if you have very limited rifting, there's lots of crustal material on top of your system, and there's very little chance for the mantle to get to the surface. However, if you have more rifting at the start, there is lots of mantle material close to the surface, and it has a chance of being caught into this mountain range and being pushed up to the surface, especially when there is some asymmetry to the surface. So one plate can push mantle to the top, on top of the other plate and to the surface. Then there is another thing that we tested, which is the tectonic pause between the initial rifting phase and the inversion of the basin. And what I show here is basically a couple of different models where we have the end of rifting here at the top, different amounts of rifting. So this would be after 5 million years of rifting, 10 million years, and 50 million years. And then I just let it rest for a little bit of time. And the obvious thing that happens is that the whole system cools down. So the hot mantle material that reaches to the surface, it starts to cool down again. So the isotherms, that are these white lines here, they start to flatten again. And so that's something very simple, I guess, but it's somewhat important, because if you start to look later on in models where we have, so this to the left here would show the end of the rifting phase, and these are end of convergence or end of inversion models. But we have different amounts of tectonic pause. So it would be either 20 million years or 40 million years or 80 million years. If you have only limited rifting at the start, it doesn't really matter that much. The model looks very similar. But if you go to larger amounts of rifting, you can see that the structures are very different if you have different amounts of tectonic pause within your initial rifting and your conversion. So that's an important thing as well. And what I try to do here as well is that I try to plot the amount of exhumed mantle, the amount of mantle that is higher than the initial top of the mantle. And there are different plots here, one for 20 million years break, a 40 million years break, and 80 million years break. So that would be the same 20, 40, and 80 that you see here. And depending on the initial amount of rifting, you get more and more mantle. So these are different models that are being plotted. You get more and more mantle that's being exhumed. Then if you have a break, it remains more or less stable, although it subsides a little bit. And then when we start to invert again, we start to compress, and then we start to push down a lot of mantle to the bottom again. So it's important then to understand within your final phase, what happens? Can we still get mantle close to the surface or not? But this is one thing that I started to do. I started to plot these kind of things, and this is something very cool, something that's very difficult in analog models, but very easy, it seems, in numerical models. So that's very nice as well. Another factor is erosion. And what is plotted here is the plate velocity. So if we move fast or, if we move slow or fast or at the reference velocity, we see that if we move fast, we move a lot of material into the mountain range. It needs to be eroded. Erosion can't keep up, so the mantle is being pushed down. The opposite happens if we have a slow motion, so that there is lots of time for erosion to take away all the material, so mantle can be just passively almost being pushed up to the surface. That's with the plate velocity, and the same thing is basically seen if we have erosion efficiency higher or lower. If we have a low erosion efficiency, we have a similar situation as if we are putting a lot of material into the system. It has difficulties eroding, and therefore the mantle remains deep. Whereas if we have an efficient erosion, then the mantle material gets to the surface more easily. So that's a good thing in our type of system. So these were some first models that I did, or some first real results. And what we find is that it's important to have longer rifting phases if you want to exhume more mantle. There's a tectonic pause that can strongly affect the system. So you've seen that you get a very different type of mountain range if you have a longer pause. And also the erosion and the tectonic plate motion can affect the mantle exhumation. And then, of course, there is the question of application. The application would be something like the Alps of Pyrenees, where you have an initial rift phase that is then being closed, but it might also be other areas around the world. But we'll have to talk about that later. That's it, I think. So thank you very much for your attention. And that's cool. Thanks.
Great. Thank you, Frank, and also Valeria and Maaike.